other than those 4 moments of inertia we already talked about, there are other quantities that could be used in descriptive statistics. So here we're talking about other measures of central tendency. Median is one, right? Median is the central value in the data set. If you have even number of items, like so, then the median is the average of the 2 middle numbers. And then you have to sort the number. So you have to sort it first, then find the average of the 2 middle numbers when you have even numbered data set, right? What if you have odd numbers? So say you're finding the average of these 5 numbers. So 5 numbers, 5 is even. It's just the middle value after sorting. So you have to sort first, then pick the middle value. So that's how you find your median. And then you'll see Python functions on how to do this. Unlike the mean, the median is not influenced by extreme values. So that's one of the advantages of the median. The mean simply adds everything, right, and divides by the total number of items in the sample. But that could be severely affected, right? If, for instance, your production data looks like this, but you add some shortens. So these will be outliers, and if this is 50,000 barrels, for instance, per day. So if you just average all the items, you'll be averaging all these zeros, and it will give you a much lower value than you want. But if you use the median, as long as these values are not in the middle of the data set, especially if it's just a few of them, so something like this, so the odds of that being in the middle is very low. It's just an outlier. Then the median is robust. It doesn't even see all of these outliers. So that's the advantage of the median over the mean. The mean will add the outlier and then divide by the total sum, whereas the median simply figures out the number in the middle of the data set. So it's robust even when you have outliers. In a perfectly symmetrical data set, which could be looking like this for normal distribution or Gaussian distribution, the median is equal to the mean. So in the normal distribution or Gaussian distribution, which means the same thing, the mean and median are the same. And it's equivalent to P50. What's P50? It's a 50th percentile, basically. So if this has on the y-axis some frequency which could be normalized, and here is the actual data. So if it's ages of students in this class, that's what you're going to have. The actual data will sit on the x-axis. This is the frequency of occurrence of each of those ages, right? So this is the probability density function when this frequency has been normalized. So all of the frequencies will eventually sum up to 1. So that's your probability density function. You could come up with a cumulative density function for CDF. So this is probability density function. This is cumulative density function. And the goal is to have this y-axis go from 0 to 1, corresponding to probability. And that one is basically 100%. And it typically looks like this, like an S curve, basically. And then this is 50%, right? 0.5. You extrapolate it to the 50th percentile, and then you can bring it down and you will find a number sitting at the 50th percentile, where this could be ages or whatever variable you are interested in. So this is the median, the data at the 50th percentile. There are other measures of central tendency too. Here we're talking about the mode, which is the most frequently occurring. In the context of this normal distribution is the peak. That's the mode. And because it's a symmetric distribution, the mode is equal to the mean, which is equal to the median. It's a poor measure of central tendency in many cases, or in most cases actually. Why? Because it's just the one realization, why this could be ages of the student. It's just the realization that occurs the most. So it doesn't take into consideration what's going on with the variable everywhere else. So it doesn't account for other elements. And that's why it's a poor measure of central tendencies. Another reason why it's a poor measure is that some data could actually have, or some data sets could actually have more than one mode. So we could have multimodal distribution. Multimodal meaning multiple modes. Bimodal distribution, 2 modes, something like this. There are 2 modes in the data. And then if you pick just one mode, then you miss this, and that will be misleading. It is also unaffected by the extreme values because it's just the single value that has the most occurrence, or that has the highest frequency. For a perfectly symmetric distribution, like the Gaussian distribution or normal distribution, which mean the same thing, mean, median, mode are all equal. So mean, median, mode all appear here. Other measures of variability, like dispersion, right? It's range. And range is just difference between the maximum elements in the data set and the minimum. So biggest number, smallest number, that's the range. For the age data set I gave you, the range will be 24 years. I believe that was the oldest student according to my guess. And then youngest student 19. So range is 5. It's not particularly useful. Why? Because it only uses 2 values in the entire data set. So if you're looking at a population of 1 billion students, the range will only use the ages of 2 students. And the question is, could that be representative of the entire distribution? Probably not. That's why it's not a particularly useful measure of dispersion. It can also be very sensitive to outliers, right? Say you have a student who is 70 years and you have a student who is 7 years, and then their range, 70.7, describes all of the information, and that could be very misleading. So extremely sensitive to the outliers in the data set because it only uses 2 values. And then those 2 values could be far from representative of the population or sample. Coefficient of variation, that is the ratio of the standard deviation to the mean. And then you can express that fraction as a percentage. That is the coefficient of variation.